Massive industrial diesel engines are designed to operate under extreme internal pressure for tens of thousands of hours. They convert heat energy into mechanical work through a constant pressure cycle, compressing air to high temperatures before injecting fuel to drive the pistons downward. On December 30th, 2024, the Dorothy Pathfinder barge was anchored in Lake Erie. At 16:05, the engine's automated logs showed a steady 1,800 RPM and 58 pounds per square inch of lube oil pressure. This Caterpillar 3516B engine was generating 2,447 horsepower. It is a massive assembly of cast iron and forged steel, built to maintain heavy electrical loads for the entire barge. 4 minutes after logging those healthy telemetry numbers, a catastrophic failure occurred. Internal components breached the cast iron engine block near the number 9 connecting rod, resulting in $2.6 million in damages and a massive fire. Tracing the timeline of the Pathfinder disaster reveals how specific, invisible physical forces can overwhelm even the most robust heavy-duty hardware. Catastrophic engine failure is rarely a random event. In this case, the structural breakdown was the inevitable result of the machine's own microscopic operating physics being pushed beyond their limits. The investigation found the failure originated in the electrical generator, where technicians discovered incinerated insulation on the stator leads near the bus bar. This caused a phase-to-phase electrical short, creating an instantaneous block load, dropping the magnetic field while electrical current spiked. The generator's voltage regulator sensed this drop and immediately maximized the output to restore magnetic flux. This expanding magnetic field acted as a massive invisible brake, applying an immediate physical resistance to the spinning rotor, trying to bring it to a dead stop. The danger of this short was the instant transfer of that stopping force directly to the engine's crankshaft, while the diesel engine was still burning fuel to maintain its speed. Sensing the RPM drop, the engine control module responded by dumping maximum fuel into the cylinders. The engine fought to accelerate against the generator's magnetic brake. This created torsional oscillation, a violent twisting force occurring when a shaft is caught between opposing torque loads. These oscillations can reach high amplitudes, placing extreme strain on the metal. The immense torque physically warped the steel crankshaft inside the block. On the Pathfinder, the peak of this twisting deflection occurred exactly at the journal for the number 9 connecting rod. When an engine software executes a command to accelerate against an immovable physical resistance, the solid hardware is forced to absorb the impossible load. Under normal operation, engine bearings rely on a hydrodynamic wedge. The spinning shaft never actually touches the bearing. It rides on a microscopic, pressurized film of oil. But the torsional warping forced the crankshaft journal to deflect, physically piercing that oil barrier. This metal-to-metal contact created enough friction to grab the bearing and force it to rotate, or spin, inside its saddle. This rotation misaligned the oil supply passages, instantly cutting off all lubrication to the connecting rod while under full load. Without oil, the friction created a hot short. The resulting heat melted the lead in the bearing, friction welding the steel components together at high speed. The seized connecting rod snapped in half, launching through the cast iron block, venting hot lube oil into the engine room and starting a massive fire. A microscopic mechanical misalignment of only a few millimeters is enough to breach the engine block and turn internal hardware into lethal shrapnel. While the Pathfinder suffered internal warping, diesel engines are also susceptible to an external failure loop known as diesel runaway. Because they govern speed by fuel supply rather than air, ingesting combustible external vapors provides an uncontrolled, unmetered fuel source. This failure can trigger in seconds, with vapor concentrations as low as 22% of the lower explosive limit. The computer shuts off primary fuel injection entirely, but the engine continues accelerating by feeding solely on the airborne vapor. As RPMs climb beyond the design limits, internal valves fail to close fast enough. This allows raw combustion flames to reach the intake manifold, meeting the incoming vapors head-on. Once this chemical feedback loop begins, the engine becomes an autonomous system that no human intervention or digital computer can stop. Managing these extreme forces requires the mathematical rigor found in modern heavy haulage engineering. Manufacturers like Scania require custom torsional oscillation calculations for every engine installation. This ensures that the rotating mass of the gears and flanges will not trigger resonant frequencies that could warp the crankshaft. They also demand microscopic precision for the hydrodynamic wedge. Crankshaft journals must be polished to a surface finish of 10 microinches or better to prevent the friction that leads to oil starvation. Other solutions focus on protecting the driveline from the shock of massive loads. Volvo utilizes I-shift transmissions with crawler gears, featuring a 37:1 ratio. This reduces the strain on the clutch by 75%, allowing a 325-ton load to move without snapping internal shafts. Heavy engineering is a constant calculation of forces. When a machine loses the balance between its power and its mechanical limits, the resulting destruction is absolute.